Hi everyone. I'm Chongyu Wang, and my partner is Wangzhe Sun. Today we choose the paper TCP and explicit congestion notification as our project. We will talk about the explicit congestion notification (ECN), which is an improvement of congestion control in TCP. First, let's take a review of the congestion control of TCP we learned in class. There are three mechanisms in TCP to achieve congestion control: slow start, congestion avoidance, and fast recovery. For the model we learned in class, TCP controls the packet flow in network by dropping the packets. Packet drops are indications of congestion. For example, in this graph, we can see um, the TCP connection first coming to the slow start phase, and then it get into the congestion avoidance phase. At this point, the queue of the router at the receiver might be full. So um, the packet is dropped, there will be a timeout, and no egg will be sent back to the transmitter. There are several problems in this congestion control mechanism. First, throughput is low in this network. The bandwidth is wasted. We can see at this point, we can see at this point, um, the packet is dropped, so the bandwidth is wasted, and the congestion window become one, then keep increasing. The bandwidth is also being the bandwidth will also be wasted during this time. The TCP connection can transmit more packets during this time, so uh, it is also a waste of the bandwidth. Second problem, when receiver drops the packet, the transmitter cannot get the information, so it just waits for the timeout. It is also a waste of bandwidth. Besides, the time of the timeout is hard to choose. If it is too long, the bandwidth will be wasted. If it is too short, the timeout might be triggered while the app is still on the way. So how to optimize this congestion control problem? The idea to solve this problem is is that before the network get congested, let the transmitter know it. Then it can decrease its congestion window the, and send less packet. Uh, there are some methods to achieve it. First, the source quench message. ICMP source quench message is an early ECM mechanism implemented in TCP IP networks. When the queue of the router is full, it will send a source quench message to transmitter. However, the source quench message is criticized as consuming network bandwidth and is both ineffective and unfair because it sends extra packets to enforce the transmitter, which makes the network even more congested. Besides, it is too late to inform transmitter when the router's queue has already been full. It's ineffective. It cannot solve this problem. So, second method is the ECN mechanism, which we will talk in this project. There are several bit ECN bits in TCP packet header. The idea of it is that the router should monitor its queue. When the set of queue is going to be full. The ECN bits in ACK header should be filled. Then the transmitter receives the ACK and checks the ECN bits. Then can it can know the network might be congested, so it decreases the congestion window size to avoid congestion. In that case, TCP network can avoid prospective congestion without sending extra packets or dropping packets.
Okay, now I will talk about the overall workflow of the explicit congestion notification mechanism. So for the mechanism to work, we need an additional negotiation stage before the mechanism being activated. And actually, the negotiation message can be piggybacked on the TCP message themselves, so there will be no additional overhead. And during the transmission, ECN aware routers are responsible for the congestion detection. So basically, if any router detects the congestion, it will simply mark the packet, and after the receivers get the packet, it will echo the congestion back to the sender. So now the sender will learn about the congestion and make some reaction to it. And obviously, simply incorporating the ECN bits into the TCP header is not enough for the whole mechanisms. So here is some general guidelines for us to modify the TCP protocols themselves in order to fully utilize the mechanism's power. So firstly, the TCP response should be similar to its response to a dropped packet in a long time scale. This means that in the long run, the effect of ECN mechanism should be the same as the effect of packet dropping, which is reduce the transmission rate. But actually, in the short run, the response of TCP with the ECN mechanism can be a little bit more radical, I would say. For example, it can continue transmitting the packets with maybe a reduced rate, even after receiving the ECN notification, compared with completely stop the transmission. And secondly, the receipt of a single ECN should trigger a response to congestion. So this is because that when a TCP sender receives a congestion notification, it can know for sure that there's some congestion going on in the path. So instead of strictly following the TCP state diagrams, it can impose some additional reaction to the congestion. For example, reduce its congestion window or reduce the slow start threshold in order to control the congestion. And the third guideline is actually somewhat related to the second one. It just being said, there's no need for repeated reaction to the congestion within a reasonable period. And typically, this period is set to be one round trip time. So if the TCP sender has recently deals with the congestion within one round trip time, it will simply like ignore any succeeding congestion notifications. And this can prevent overreaction to the congestion and help improve the overall traffic. And now let's talk about the advantages and disadvantages of using ECN mechanisms. There are two main advantages of the mechanism. So firstly, it can help avoid unnecessary packet drops. This means that when using ECN mechanisms, the routers will not like discard random packets on the path in order to reduce the congestion. And this will definitely help reduce the packet drop rate and reduce the packet delay while improve the overall traffic at the same time. And this advantage is most prominent in a highly congested network where there will be a very high chance for the routers to drop packets on the way in order to control the congestion. And the second advantage is the prompt congestion notification. This means that for the TCP senders, when it receives the acknowledgement messages from the receivers, it can know immediately and for sure whether there is a congestion going on the path or not. And this is actually a pretty valuable information to know about, since it allows the sender to directly act to the problem itself instead of like guessing whether the packet loss is caused by congestion or bit corruption or maybe some other reasons. And for the disadvantage side, the most weakness of ECM mechanism is that it is actually a little bit less reliable than packet jobs approach. This is because that the ECM mechanism relies on the successful delivery of TCP messages. So if TCP messages fail, like maybe get dropped on the road, there's no way for the TCP sender to learn about the congestion and make a reaction to it. So compared with ECN mechanism, even though the packet dropping approach is much slower, unfortunately it provides a more reliable mechanism for congestion control. And this is basically for our presentation about ECN mechanism. And this is our reference. And thanks for listening.